Yeah, okay. So our today's lecture starts with Carlo Rovelli. I think I don't have to lose many words about Carlo himself. And he will be talking about black to white hole transitions.
Wonderful. Thank you, Johannes. Thank you, everybody, all of you. It's so bad we cannot go together. I would like to know these young people around and have an opportunity to meet each one of you and chat. The school was meant to be in Marseille this year. I hope there will be another opportunity. I would much like if I could see some faces instead of if all of you who can keep the camera on. Hi, Sina. I see people. Hi, Sebastian. So I don't have the feeling of talking to nothing, to a dark cloud, and it doesn't consume more Wi-Fi in this way. Good. So I'm going to. We have a couple of hours. It's sort of too long to be a conference lecture, but too short to be a real class, a real course. So what I'm going to do is to tell you what I've been doing in the last period, trying to understand what quantum gravity tell us about black holes. That's the topic, and it will be not so much about calculations or specific technical details. There will be a few technical points which are emphasized, but a number of ideas. A number of things I've learned from various people. Some are in the audience also, and another thing I realized that I think are wrong ideas floating around, and the perspective I think we can have from quantum gravity about black holes and what we can do about loop quantum gravity, with loop quantum gravity in particular. So toward the end, especially, I will tell you how I think we can use loop quantum gravity specifically to get information about the physics of black holes. And for those of you who were present at the panel yesterday, there was a discussion on where to go, what is most urgent to do. This is the spirit of what many people said, let's do physics, not just mathematical physics. At least for those who like to do physics, not mathematical physics. So not just refine a mathematical model. My opinion is that there is a very good mathematical model out of there for quantum gravity, which is loop quantum gravity. I worked more recently in the covariant formulation. So there is at least one specific well-defined set of transition amplitude. There's a theory, which is ultraviolet finite, and which it's Lorentzian, is in 4-dimensional, is what we want. And so there are many open questions there, but it seems more urgent to me to apply it. And this is why about the last 5 or 10 years I've shifted a lot toward applications. And there's a lot of work in cosmology, but I've focused on black holes. And black holes are fantastic. I mean, it's hard not to be fascinated black holes. Now, before beginning, let me say that I have 3 books. 2 are out. One is 2004, one is 2014, and one is coming out soon. 2 about loop quantum gravity. And the third one, which is coming soon, is just an introductory course on classical general relativity. It's a short introductory course on classical general relativity. And they all 3 are free online PDF. So please don't tell around because if my various publishers know that, they kill me because they lose money. But I don't write books to make money. I write books to to diffuse ideas. So I don't care about money. I want people to read the books. The first one, Quantum Gravity 2004, it's a detailed discussion about all the conceptual basis of quantum gravity. What it means to be a quantum theory of space-time, what it means that you don't have a time evolution, what it means that space comes out from the quanta and not vice versa. For those of you who want to enter into quantum gravity, I recommend it because it's I think we're building on a number of ideas, of course, not just mine ideas, ideas of many people, which make this non-perturbative approach to quantum gravity, which is quantum gravity, solid. And it is because there's this a long conceptual discussion. Maybe it's not over, but one young person who want to work in quantum gravity and give a contribution to quantum gravity, I think should know that. The second one, it has the complete definition of the transition amplitudes in 4 dimensions, Lorentzian, and it's much easier. It's a more introductive course. And the third one, I mean, it's not quantum, it's just classical general relativity. But I think that classical general relativity should be learned, should be taken from the right perspective to be able to do quantum gravity. And the right perspective, in a word, is reading Einstein discovery not in the sense that gravitational field is space-time, but the other way around, reading it that space-time is the gravitational field. And this is how Einstein ended up thinking about the theory after changing his mind various times. I think this is the right perspective. The book is written for that perspective. Various of the specific points I will make in this lecture in that book as well. But so get the books for free. Black holes. This is a plan. What do we know from nature about these things, black holes, what we know from general relativity, and what we know from loop quantum gravity. I will not follow strictly this line. I will jump a little bit back and forth, sort of obviously, but this is all what I will cover. So let me start from the first thing, what we know about black holes. There was a time in which any lecture about black holes started from mathematics. I think this time is over. I mean, these are our grandfathers, because mathematics can be misleading. I mean, we don't know. The things are out there, and we don't have the full theory of nature. On the other hand, we have impressive, overwhelming evidence, uncontrovertible evidence that there are those funny things up in the sky, which we call black holes. Okay, so a black hole, by definition, is, for me, is that things we see up there, out there, okay, which might or might not be described by general relativity to some approximation. And the evidence is overwhelming of all sorts of black holes. The first discoveries were the stellar black holes, of course, but the most impressive are the galactic black holes. This is Sagittarius A star, the one in the center of our galaxy. In fact, I said something wrong. The first recognized were the stellar black holes, but the first detected was Sagittarius A star, our big black hole in the center of our galaxy, because the first radio signals that, you know, when people just almost by chance started pointing radio plates toward the up rather than toward the horizon, they got a signal. And so it's immense. If we had eyes tuned to radio waves, the only thing we would see is the black hole at the center of the galaxy. It's a very strong signal. And then we discovered that there is any galaxy one. We have a picture of one recently, this one, which is 1,000 times bigger than the one in the center of the galaxy. It's more visible because it's 1,000 times more distance, but this is roughly 1,000 times bigger as mass. So the one inside of a galaxy is 1 million solar masses or 4 million solar masses. This is 1 billion solar masses. And we have huge evidence that there is something very peculiar there. There are the orbits of the stars, the Keplerian orbits of the stars around it that tell us that there is this enormous mass concentrated in a very small region. Then, of course, there are the gravitational waves, which have been detected, and whose interpretation is again in terms of black hole. There are many gravitational waves. These are all the ones, all the things that LIGO and Virgo and have detected. These are others which are most probably merging of black holes. And if you think these are couples of black holes. So if we see so many couples of black hole merging, it means that there are zillions of things outside. And of course, recent Nobel Prizes are all recognized as spectacular advances in our figuring out what is out there in the sky. Now to question how big they are and how many they are. I mean, how big they are, we really don't know, because we had first evidence for stellar black holes formed by a collapsing star which are a few times the solar mass. Our sun is probably too small to become a black hole, but a bit bigger star ended the life in a black hole. And then we realized that this thing, the center of the galaxy, it's which is 1,000,000 times larger, is a black hole, and we found this gigantic black hole, 10 to the 9 or even 10 to the 10 solar masses. There is some evidence that there are intermediate ones. I'm not going into the astrophysics of that, just to mention that. And of course, there may be smaller black holes. I mean, we keep discovering black holes of different size. Presumably, the quantum, the Planck mass, which is a bit smaller than a microgram, it's a lower bound, and it's possible that small black hole or Planck mass black holes were produced in the early universe. There's a lot of work about production of black holes there. So black holes might cover 10 to the 50 or 50 order of magnitudes, 50 order of magnitudes of a spectrum. And we have no idea how many they are. There's an estimate just of the supermassive black hole, the galactic one, which is 10 to the 11th, because most galaxies seem to have one. We don't really have an idea how many are stellar ones in our galaxy. So they're all over. And it's a major component of our universe, so to say. And, 20 years ago, people didn't believe they existed. Now, what do you know about them? Well, first of all, general relativity gives a fantastic account of practically everything we see about black holes. In fact, it's more than that, because it predicted those, okay? They were predicted by, not were predicted, it was predicted that we could find, they could exist and could find them just on the basis, essentially, of the Einstein equations. These are the Einstein equations. I want to stress two things. There are two constants in the Einstein equation. One is the Newton constant, which comes with 8 pi. And just let me remark that some people use 8 pi g as a gravitational constant, which may make sense. It's the thing in front of the action. It would naturally be 8 pi g. I'll come back to that. And then there's a cosmological constant, which is a constant in the Einstein equations. So gravity depends on two physical constants. The idea that this is just a product of vacuum fluctuations, I think is silly, in my opinion. All constants are corrected by radiative correction. So G, lambda, all the constants of the standard model are corrected by radiative correction, but they're constant of nature. And we have to measure them and imagine that this is a funny phenomenon called dark energy with a mysterious source. It's something which is misleading, I believe. Just a quantity which we don't know well how to normalize. Now, one solution of the Einstein equation is, of course, the Kerr-Newman metric, which is the quintessential black hole metric. Careful, this is the static black hole metric, right? All the black holes that merge, that we see in the sky, where things fall in, are not exactly described by this metric, of course, because things move, things fall in. There is the effect of the stars going around, but in the limit in which you disregard what matter does or what another black hole hitting does, this is seems to give a good description, and more importantly, the idea itself that the mass can collapse and create an horizon is it's well accounted by this metric. In fact, it suffices to look at the Schrdinger metric. The Schrdinger metric, I believe all of you know it or recognize it. This is in G equal 1, not 8 pi G equal 1, and the mass of the black hole is little m. Now, as you know, the Schrdinger metric has singularity at r equal to m, where this is 0 and this diverges. But this singularity is really, as you know, a coordinate singularity. The easiest way of thinking about is take the Cartesian plane with x and y coordinate and define a capital Y coordinate is 1 plus 1 over x. And it's constant y lines are these lines here. You see, they avoid this point here. They avoid this line here. So this line gets stretched. If you go to coordinate capital Y, little x, you throw all this point to infinity in this coordinate. You just throw them out. This is what happened to the t coordinate in the Schwarzschild metric. So in other words, r equals 0 is like x equals 0 here. Is not the line r equals 0 in the Schwarzschild coordinate is not a set of points. It's a single point expanded. So as you know, we know how to Q them. We go to Kruskal coordinate. This is a metric in Kruskal coordinate, UV. It's easier to squeeze them in a picture using coordinate U tilde and V tilde, so that you go minus infinity plus infinity, UV, U tilde and V tilde goes from minus pi half to pi half. So all space-time you can draw in a little picture here, forgetting the angular coordinates, and the original Schwarzschild coordinate are this one. The T ones, a constant T are these lines here, and you see they avoid the horizon. To go to the horizon, you have to go to T infinity, exactly like in here. To go to x equals 0, you have to go to capital Y equal to infinity, but you know, it's just because you have chosen silly coordinates. And inside, the role of x and t as space and likely it's inverted, which has no particular meaning whatsoever. It's just, you know, coordinate or coordinate don't mean anything. Where you call one r or t is just it just names, has no meaning whatsoever. Now, what has this to do with the thing within the sky? Well, we believe that if there is a star, the outside is well defined, is well described, the limit in which non-rotating, by this metric here. So if this is the border of the star, which starts from some radius and decreases the radius, goes smaller than r equal to m, the outside part describes what is outside the star, right? So there's exterior, the horizon, and the interior of the black hole. Good. So this is therefore the picture we have, just drawn a little bit more straight. The black thing is a star. This is horizon. This is all the sky minus, all the direction you can come in from infinity. This is sky plus, all the direction you can go out from infinity. Now, since I'm here, and since it will play a major role, let me notice that the Kruskal solution has also a white hole and another asymptotic region. And the white hole could also represent something in our universe if we think a star which is bounded, the boundary of the star doing that, an expanding star, an exploding star, for instance. So not something that falls into the black hole, but something that comes out from the black hole. So in other words, this is a possible solution of Einstein equations apart from the singularity, and this is also a possible solution of the Einstein equations apart from the singularity, okay? So this is a star following the black hole, this is a star coming out from a white hole. And you may say, well, white holes are not there. Of course, and people have been saying black holes are not there for 70 years. In fact, when I was hired in Marseille, my director said, you don't believe that black holes are real, right? I mean, you relativists have this strange idea, but I'm a particle physics. I mean, it doesn't make any sense. And even Weinberg, in his book in the 74, was already evidence of sinus X, 1, whatever, still writes that it seems implausible that black hole exists, but black holes exist. Well, the only account that we have of the phenomenology that we see is in terms of this mathematics here. So black holes have been discovered, white hole might be discovered. Let's leave the possibility open. What's a black hole, white hole seen from the outside? Think about Kruskal. If you're outside, take a constant r, a little bit larger than 2m, as 2m plus epsilon, with epsilon small that you want. You don't know whether you're outside a black hole, outside a white hole. It's the same. Okay, so all the physics outside a black hole is the same as physics outside a white hole. The difference, if it's just look outside, is that you sort of see things disappearing into 2m plus epsilon in a white hole naturally, and you see things coming out from a white hole. Good. So this is what we know, and let me stress that everything we see is well accounted by general relativity, and the kind of things you can do with variations of Kerr metric. Kerr-Newman is not needed because these are not charged, and with doing numerical relativity, studying what happened when you excite this matrix and black hole merge. But of course, there are things we don't know, and two things are clearly open. The first is what a child would ask if you tell the story of black holes to a child. Namely, most of the signals we see, these radio waves that we see, are because of accretion disk, things that fall into the black hole. So we see literally matter spiraling toward the black hole and disappearing. Okay. Recently, there was a big cloud that went very close to Sagittarius A star, and everybody was saying, is it going to fall in or not fall in? Apparently, it did not fall in, but it was disgregated, and maybe there is a recent flare in a Sagittarius star, so maybe a part of it is falling in. And the question is, where does it go, right? Our theory doesn't tell anything about where does it go, because if matter falls, it goes through the horizon. We know exactly what's going to happen, and then there is a singularity where the theory doesn't work anymore. So that's the first question. What happened if you jump in? What next? Or what happened to the star that collapsed? What happened to it? And the second is what happened to the black hole. If you just leave in a black hole there for a very, very long time, what is happening to it? And we have reasons to believe, strong reasons to believe, that it's not going to be eternal. And I'll come back in a moment.
Sorry, Carlo, there's a question.
Yeah.
The question is, so as the student understands, the white hole is just the byproduct of the cross-call extension. So why can we view it as a real physical object?
I think we should view it as a real physical object. We definitely should view it as a possible real physical object. It's a solution of the Einstein equations, which might describe something real. Of course, we don't know. Like, we didn't know before if the black hole solution of the Einstein equation described anything real. It turned out to do.
Okay, thanks.
Now, why are we confused if we have such a good theory like generativity? Because there's quantum phenomena, of course, and generativity by itself does not include quantum phenomena. Phenomena are two kinds. Quantum matter effects on the gravitational field of a black hole, and quantum phenomena of the gravitational field itself, of space-time itself. This should not be confused. The first, we have a decent theory. The second is quantum gravity and loop quantum gravity. So let me say something about the Hawking radiation first. I'm not giving a course on Hawking radiation, but there are a few points I want to make. So first of all, on the space-time geometry of a black hole, if you have a quantum field, and if you start off in a vacuum state, no particles, particles are produced. And there's a celebrated calculation by Hawkins in which he shows that these particles at infinity, if you wait long enough, you start seeing a thermal spectrum, so a Planck spectrum, with this temperature here, which is a Hawking temperature, which in unit h bar equal 1, c equal 1, 8 pi g equal 1, and Kelvin, how's it called, Boltzmann constant k equal 1 is just 1/m, quite remarkably. Now, careful, because this is often confusing. Every curved space-time produces particles, right? It's not just a black hole. So if you take arbitrary curved space-time, it starts from a vacuum, you evolve, except particular cases, you have to be very, very careful to have a space-time that does not produce particle, generically produces particle. Why? Well, because there's a gravitational force. I mean, you take the field, expand in modes, its mode is an oscillator. You start in the vacuum, there is a force, you push it, and then it starts oscillating, namely they're quanta, and the quanta are particles. So the fact that a black hole produces particle, it's obvious to anybody who understands the basics of quantum field theory. So what was the surprise in Hawking calculation? The surprise is that you get exactly a Planckian spectrum. It's a thermal spectrum in the limit in which you wait long enough, right? So the surprise is the thermality, not the fact that there are particles emitted. This is important because people get endlessly confused about that. In particular, Hawking calculation is delicate and complicated in terms of particles, but careful. Hawking calculation is all about what happened near the horizon, but careful, because particles are produced where there is curvature, not necessarily near the horizon, okay? And in particular, let me emphasize this point. I ask you a question. What's the wavelength of this radiation? Well, I mean, it's a Planckian, so it's a Planck spectrum. It has a maximum and sort of it's around the maximum. Where is the maximum? You do the calculation and you just take Planck formulas, but you know, this is physics. There's just one constant here, m, and g is floating around. So the only possibility is that the wavelength of these things is the gm, which is a Schrdinger radius. So the Hawking radiation is waves with a wavelength, which is Schrdinger radius, right? Which means that it's a phenomenon that is of the size of a black hole itself. Is not a microscopic phenomenon in a little point of the horizon. The horizon is sort of a sphere. If you go to point of a sphere, you can't produce Hawking radiation there because you need something of the size of the sphere itself, right? Which, by the way, shows that the Hawking radiation is compatible with the fact that if you go to a point, you could still see the vacuum because you don't see those long wavelengths. You would need an antenna as big as black hole to see it. Okay. So it's a phenomenal scale of black holes. Is not produced on the horizon itself; is produced around it. And it's the curious part is that is thermal. That's to be understood. Of course, if you have a temperature, you can give a thermodynamical description, and you get immediately an energy by taking the derivative of the by imagining the entropy as the temperature is the derivative of entropy with respect to energy. And the entropy is the area. Usually the area is A/4 in natural units. I just want to observe, it's a trivial observation, that if you use not G = 1, but 8 pi G, which is a natural coupling constant of gravity = 1, the entropy becomes 2 pi A, which is much more reasonable and less strange than the A/4. So this strange 4 is just 2 pi over 8 pi, 8 pi being the wrong historical conventions about the gravitational constant, coupling constant. It's not that this explains everything, but 2 pi A, it's a little bit nicer than A/4. Now, next, of course, this calculation is, Hawking calculation is done neglecting the fact that the matter itself react back on gravity, so this back reaction, right? If there's a force pulling the pendulum itself is acting on the field. And since energy comes out, you expect the mass of the black hole to decrease by energy conservation at infinity. And in fact, it's a super easy calculation. The spectrum is thermal, so the power of a thermal spectrum is the area of the emission surface, which is the area of the black hole, which is m squared, times the temperature to the 4th. This is standard black hole radiation theory. So times m to the -4, which gives n to the -2. So this is how the mass is expected to decrease. You bring t on the other side, m on the other side, you integrate, and you get t proportional to m cubed, which means that the time it takes a black hole initially of mass m to decrease to 0 if of order m cubed in Planck units, which is very, very long, right? If you put g and h bar and c inside, m cubed for a stellar black hole is many, many times the life of the universe, but not so for a small black hole. So for a small black holes, producing the primordial universe could very well be already at the end of the evaporation. So that's all I want to say about Hawking radiation. Let's come to what interests us most, which is quantum gravity effect. That's where I want to get at. And the key point is, where are the quantum gravity to be definitely expected? Okay. The simplest, I'm going to challenge this in a moment, but the simplest possibility, or at least the minimal possibility, where you really would be surprised if they're not quantum gravity effect, is when the curvature R is Planckian. By curvature here, take any scalar, take the Riemann curve, the square of the Riemann curvature contracting or indices, take the square root and call this R. This gives an estimate of the amount of curvature, which does not depend on the coordinates because it's a scalar in this sense. And when this is all of Planckian order, and this the dimensions length to the -2, so when it's a Planck length to the -2, then is when you expect the quantum gravity to come in. And where does this happen? Well, of course, near the singularity, the curvature grows, because curvature goes in Schrdinger like the mass over r cube, right? Because it's the derivative of it's a tidal force. So it's a derivative of the Newton potential, which is a derivative, sorry, the derivative of Newton force, which is 1 over r square, which is a derivative of the 1 over r, which is both in the Newton potential and in the Schrdinger matrix. So m over r m cube is 1 over m square, or 1 over r square. So you expect that this grows as 1 over r square when r grows, when r becomes small, as r to -2 when r becomes small and becomes large here. But careful, not just inside the black hole, also outside the black holes because of Hawking radiation. And this is a key point which is disregarded in 9/10 of the literature on the subject, but it's absolutely crucial. If because of black reaction, the radius becomes small, 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 at some point the radius becomes of the order of the Planck length, okay? Which means that the curvature outside the horizon, it becomes Planckian, okay? Which means that you're definitely in a quantum gravity phenomenon, which means that you cannot continue the evolution classically because something quantum gravity happens. You might make an hypothesis, but it has to be backed up by quantum gravity theory, or might be relevant. In any case, you're making an hypothesis about quantum gravity. But the requirement for the horizon to go to infinity is part of the definition of an event horizon, if you think about an event horizon. So to say that the things out in the sky, the real thing in the sky, have event horizons, is to make a statement about quantum gravity, which is most likely to be wrong, because why should this Planckian curvature outside the horizon not have any effect? Okay, let me be more precise here. For those of you who do not have a clear idea about the distinction of different kind of horizons and what it means to be an event horizon, a trapping horizon, a dynamic horizon, let me just spend one transparency to clarify this point. Because I think this is a mistake we make in teaching general relativity, in teaching classical general relativity. Take the Schrdinger magic, okay? Something happened at r equal to m, okay? What exactly happens at r equal to m, okay? There's no singularity because locally we have seen you can change coordinates, go to Kruskal, locally is Minkowski, nothing funny happens. But something happens, right? Something definitely happens at r equal to m. Two things happen, okay? And let's distinguish these two things. One thing is that the light cones, here they are, inside the horizon, both this light ray and this light ray have decreasing radius. Outside, this has decreasing radius, this is increasing radius. So the one going out is called the outgoing. So this is called the outgoing, and this is called the outgoing. So the outgoing has increasing radius outside, and the outgoing has decreasing radius inside. The terminology is a little bit misleading because sometimes one thinks ingoing, so the radius becomes small. No, I mean, this is ingoing, outgoing, this is outgoing, and the radius still becomes smaller, okay? Remember, this point here is a sphere. So imagine a sphere is flashing for a moment, just becomes super hot and makes, outside there is a light front that goes in, smaller radius, a light front that goes out, larger radius. Inside the horizon, both go in, which of course means that the sphere itself also have to go in because of course it's collapsing itself, which goes in even faster because it goes time-like, okay? The horizon is the boundary because the region, which is called trapped, that's the definition of trapped region, where the outgoing rays have decreasing radius and the other ones. It takes two lines of mathematics from here to find the null rate and discover that this is a property of R equal to M. Just 1 second. Anzi, lo metto nella camionetta nera che è aperta la porta, la Land Rover. Sì, grazie. Sorry. So this is a property of R equal to M. It's a boundary between the trapped region and the non-trapped region. This property has nothing to do with what happens in the future. It's a local property, not local in the sense that you're in an arbitrary small region. Local in the sense that you're in a finite region. Okay, it's a region of the size of the horizon itself. Okay. Now also, R equal to M has a property which is an event horizon. Namely, if you send light, it doesn't go to infinity; it falls into the black hole. But an event horizon, it's a property that depends on what happens in the future. So depend on quantum gravity. What do we know? We have to know quantum gravity. So we should stop teaching that black holes are event horizon. Black holes are trapping horizon. That's for sure. I mean, to the extent in which we believe GR. Whether they're event horizon or not is something that, you should ask people to do quantum gravity, or you should wait. We are sure about quantum gravity. And in fact, I think they're not. There's no event horizon out there, as I'll say in a moment. I'll skip this. So this is the conclusion. Because quantum gravity comes in outside the horizon, to say that the black hole horizon is an event horizon is a guess about quantum gravity, which is most likely to be wrong. Good. So now we know where quantum gravity comes in all this region here, including outside the horizon. Okay. And now let me say, this is a picture, apart from the details, which you find very often in many people discussing black holes and information problems and so on. This picture is total nonsense, because this makes, the idea here is that black hole become very small, and then it, boom, it disappears. And after it, you just have a flat space-time without nothing. The logic here is, well, it becomes very small, a little energy, and then, whoop, it pops out of existence. But this, whatever happens here is a quantum gravity phenomenon. So to believe this picture is to believe in a prediction of quantum gravity, which I don't know any theory, any of the current quantum gravity theory that predicts it. So where does this picture come from? It's just nonsense. In fact, as I'll argue, this picture has no ground. Now there's more that we learn from the classical theory. And let me start to go into the direction of what we can say about the quantum gravity region. Let's see what we can say just before the quantum gravity region. So we can trust generativity until this blue line, so to say. Let's look inside. Okay, inside the black hole, this line here. Of course, it's a three-dimensional surface, right? It's a sequence of spheres. Inside, we can take this to be R equal constant for R just before we enter into the curvature beam Planckian. So this is a Schwarzschild metric. You put the R such that just before the curvature is Planckian, which, by the way, is not the Planckian R, is much larger. And you get the metric of this thing here, which is this one here. And this is easily to read because it is a sphere times R squared and then a line element times 1 over R. This is a cylinder. It's a sphere times becoming smaller and smaller because R becomes small as you go up, times the length of the cylinder, the axis of the cylinder, which becomes larger as R becomes small. So this is a cube becoming longer and longer and longer. Careful, finite. Right? Wherever you start from, you end into the star. You always end into the star. And there is this finite tube which becomes longer and longer and longer as you go up sort of in time, smaller and smaller. How long? Let me just make this calculation. Take a stellar black hole, not one of these galactic enormous black holes, stellar black holes like Sinus X1. I mean, plug the numbers and wait until it is just before the end of the Hawking evaporation. And let's see how long this is. This is 10 to the 75 light years. So this is a right intuitive picture about inside the black hole. Of course, it depends on the choice of a foliation. Here I'm choosing a foliation which is roughly constant R inside, which is a natural one you can think inside, okay? So a stellar black hole that undergoes a long evolution at some point has this immense tube inside, very, very small, teenier, teenier, and teenier, not Planckian size, still much larger than Planckian size, still macroscopic in that sense, but 10 to the 75 light years. The volume increases because the length increases faster than the shrinking. So there's a huge volume, enormous volume, super long length, and then squeezing. Now, this immediately suggests that when you hear what happened at the star and what happened at the horizon are spatially separated, it's really space-like direction, of a huge amount, which if there is any locality in the world means that what happened at C, what happened at B is independent. And if you're in the middle, the fact that there is a star on one hand and the horizon on the other hand, it shouldn't bother you because of locality, right? So to understand the quantum gravitational property of black hole, it's really to understand three different physical phenomena. One is what happened in the middle. If you're here, what happened next? A separate one is what happened at the horizon. At some point, quantum gravity comes in. And the third one is what happened to the star, okay? So the star, the middle, and so the quantum gravity of black hole is three physical problems. A star which is super compressed to become Planckian compressed, a space-time that has this long tube and the curvature becomes Planckian, and the horizon, which at some point enter in a region where sooner or later, something quantum happened. These are the three problems of black hole, quantum gravity of a black hole. And I've been talking for 45 minutes before actually going into discussing this problem one-to-one. I think it's a good point to pause, maybe take a few minutes, because what I'm going to do next is discuss C and then A and then B and tell you what we know about each of them. But if you have questions, this is going to be a good moment.
Yeah, so far there are no further questions in the chat, but yeah, let's wait some more minutes.
Why don't we still take a couple of minutes break? And we start again in 5 minutes.
Okay.
So we can breathe. Everybody can take a cup of coffee or whatever.
Okay, let's do it like this.
And if you have questions, come back with questions.
Okay. The question is, what is the difference between the Unruh effect and the Hawking radiation?
This is a good question, a super good question. They are extremely similar. Whether one can look, I can derive the Hawking formula in the following way. If I stay very close to the horizon, to stay static very close to the horizon, I have to not fall in, of course. So I have to have rockets. So I stay close to the horizon with rockets. So I'm constantly accelerating with respect to a free falling frame. Okay, fine. So I can think that I'm in locally near the horizon, I am in a Minkowski, right? But I'm accelerating. Let me assume that I'm in Minkowski in the vacuum and I'm accelerating. Let me take it as an assumption. Because of the Unruh effect, the Unruh effect is the fact that an accelerating observer in vacuum in Minkowski sees particles. This is a Unruh effect. And it's a straightforward calculation that can be done in 10 different manners. If there's a quantum field theory and the state of the quantum field theory is a vacuum, you accelerate and you have a detector that will get excited and sees particles, not only sees particles, but sees thermal particles at a temperature which is determined by the acceleration. So I see particles and at a certain temperature. So I'm here, I'm accelerating, I have a thermometer, say, oh, look, there is a temperature. Now, this temperature depends on the acceleration, and that acceleration depends on how far I am from the horizon. So the temperature depends on my distance from the horizon, and it becomes bigger if I'm closer to the horizon because I'm accelerating more, and less if I go away from the horizon. And in fact, the way it changes with distance, it's consistent with what is called the Tolman law, which says that anything which is in equilibrium in the gravitational field, if you take water in equilibrium in the gravitational field and you go to equilibrium, the temperature is going to be a little bit higher down, a little bit lower up. This is another beautiful calculation. It's statistical mechanics in classical general relativity. So you know how it scales by going away from the mass. So you can use the Tolman law and say, how does this temperature scale, and move it all the way to infinity? And you get exactly the Hawking radiation. You get the Hawking temperature, exactly. So I could derive the Hawking temperature from the Unruh effect and the Tolman law. So obviously the two things talk to one another very, very well. And there is a lot of similarity in the two. However, to say that the Hawking radiation is nothing else than a Unruh effect, it's probably overstressing because the Unruh effect is just an effect of how we move, while the Hawking radiation, it's actually something where there is an energy momentum tensor which is different from zero, and actual particles that move around in space-time. So I think that to conclude from what I said before, okay, so there's nothing to understand about Hawking temperatures besides the Unruh effect. It's missing some physics.
Okay, thank you.
Should I restart?
There are more questions.
Okay, let's go to the questions.
There's one double question. It's about the volume of space-time growing with time beyond the horizon could be connected to the information loss paradox.
Yes, I'll get to that.
In the sense that the information exists in this region, but it's not reachable due to the trapping horizon.
Yes, is exactly right, and I'll talk about that in a moment.
Okay, and then there's following on this question, it's asked if this region of space-time growing with t beyond the horizon can be considered as an independent universe.
No, I see no reason at all for seeing it as an independent universe. It's just behind the horizon, but it's not an independent universe. I'll come back to that also. I'll say more about that.
Okay. Okay, so then there is another question. It's regarding white holes. I agree with you, white holes should not be ruled out, but my lecture claims that it violates some information conservation, cosmic censorship, question mark. I was wondering, how would you respond to this?
I don't think they violate anything. In fact, there is a sense in which they violate the cosmic censorship hypothesis. It's true, but there is no reason to expect that the cosmic censorship hypothesis is true in quantum gravity. Again, let's. I'm going to address that in the second part of the lecture.
Okay.
All these three questions.
Okay. Yeah. Then there's one more question about the black hole horizon, and the question is if it's possible to describe the black hole horizon completely locally.
Yes. Yes. In fact, if you think about the solution of the Einstein equations in just write it in Kruskal coordinates, for instance, this is a local description. Namely, you can expect this to go wrong in the future, but whatever happened here is perfectly well described by the metric, and the properties of the horizon, like being the boundary of the trapping region, are well described locally. The people who do numerical simulations for helping LIGO to detect they know where the horizon is. They have a code in the machine that says here is the horizon. It's local. Now, of course, one should be careful about what one means by local, because in general relativity, if you go very local, everything is just Minkowski, right? So to detect that there is a trapping horizon, you have to look at the region of the size of the curvature, of the size of the black hole. Somehow you cannot go in the limit in which you are just Minkowski. But as soon as you as you have a region large enough, you just flash some light and measure the area of the growing flash, and if it decreases, you're inside. If it increases, you're outside, without expecting anything about the future. And that selects the horizon.
Okay, thank you. Yeah, I don't see more. So there was a question if there's time for more questions, but then no question was posed. So
okay, okay. Let me go ahead. There will be time at the end of the lecture. Okay. So where I arrived is the idea that there are three different problems here. And let me say what is known about the three different problems a bit fast, but focusing on the main idea. Let me start from C. Okay. C is a problem of a star. So some mass, which becomes smaller and smaller and smaller. And at some point, the curvature becomes Planckian and the density becomes Planckian. And the Einstein equations connect the density and the curvature. Roughly, the curvature is the order of the density. So at some point, become Planckian. Notice again that this happens. This is sort of intuitive picture. There's this long tube, which is longer and longer and longer. So it happens at an incredibly long distance from the horizon. It's far, far, far away. Okay, a lot of time has passed outside. If you fall in the horizon here, you're falling in much later than the star. And inside, somehow this has translated in extremely long tube. The proper time between here and the singularity is short, but the proper distance along the line is enormous. Okay. Now, there is a lot of literature about oh, I'm missing a slide, sorry. So I'll go inward. There's a lot of literature about collapsing stars, which I'm not gonna come back here, in quantum gravity using symmetry reduced models. So you just take a sphere and you see it's decreasing. And one of the biggest experts in this is our chair, Johannes Munch, who has worked a lot on that. And there are a number of indications that go exactly in the same direction of what happened in quantum cosmology. Quantum cosmology, you have a universe with a certain density, you evolve back in time, the density grows, 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 and what happened, the quantum phenomena that comes in the reducer model is essentially you develop some pressure. The curvature is bounded. That's one of the main predictions of loop quantum gravity, that the curvature is bounded to the Planck scale. So you cannot grow over. And then what happens is that you bounce, okay? I'm not going to review all this literature. If you want a reference, just look for Johannes Munch in the in the literature, and you'll find. And in fact, his papers have also very good and complete references. But the outcome is that you expect the star wants to bounce. Now you say, how can it bounce? There's nothing to bounce out. Wait, let's just put it as a indication that what the matter would like to do dynamically is to not go all the way to zero radius, but at some point to start bounce. And let me instead go immediately to the A region, which is in this context the interesting one. Now, the A region, as I said, is independent of the star, independent of the horizon. So we can just look at the inside, forget the star, forget the horizon. So we can think about the entire Kruskal space-time and think what could happen next entering the singularity. And there is an old idea which goes back to the 50s, which has proven to be extremely solid against all sort of variation. And the first who suggested is Schrdinger in the 1950s, who observed that there is a natural continuation across the singularity from the Kruskal solution to a second Kruskal solution. There's a natural way of gluing from one to the other. And I'll tell you a couple of ways of doing this. But let me anticipate is at the point that you get the same gluing, whether you do a simplified model, where you do a certain way of viewing the full theory, where you do a canonical quantum theory, or whether you just smooth out the singularity in some manner. So let me start from the simplest way, which is the following. It's a little calculation. Just look at take as equal tau surfaces, the R equal constant surfaces here. So use as your time variable the R coordinate, the Schrdinger coordinate, and these lines are constant R coordinates. Is this tube, the foliation of the tubes, okay? Now, by symmetry, the metric has this form here. It's the symmetry of the sphere, the x, and the tau being the radius, remember. Now you can take these three variables, and they all depend on tau, of course, they change with tau, and plug it in the Einstein equations. But instead of doing that, let me change variable. Careful, not change coordinates, change variable. Instead of using GTT, GXX, and G theta theta, the component of the metric, let me work with combinations of this. So introduce three variables, A, B, and N, such that A is just G theta theta, which is has to be positive here, of course, is a sphere. The radius of the sphere. So let me call A square. And GXX I call B over A, and G tau tau is A over B times N square. Okay, and then I use variable A, B, and N. So I take this matrix, I compute the curvature, plug it in the action, and I get a very simple formula. And I get the equations for A, B, and N, which are these equations here. And one is a constraint equation, like always in GR. I solve these equations. Here is a solution. And I write a metric. And this metric, I discover, oh, this is Schwarzschild. I just rediscovered Schwarzschild in a funny way. And in fact, the change of coordinate of Schwarzschild is that tau is, as I said, the Schwarzschild radius, and x, which is this direction here, is the Schwarzschild coordinate t, which I remember is just labeled this direction here. So the constant t lines are radial lines like here. So what I've done, I've just rediscovered Schwarzschild in another way. Well, wait. Tau equals 0 is a singularity. And look that the evolution across tau equals 0 is completely regular in these coordinates. right? I mean, a tau is just tau square, is regular, and this is regular, and this is regular. A tau square again. So this means that in this coordinate, the Einstein equations that go through and continue this way. What's going on? Suppose you have a pendulum, an harmonic oscillator in the variable x, and you have a differential equation, x double dot minus x equal 0. And then you say, oh, I change variable, I use 1 over x. And then, of course, you have the solution, but the solution explodes at when the pendulum is down. Oh, it's horrible, it's just funny, the universe ends, the pendulum explodes. No, you just have the wrong variables. It's not 1 over x the right variable, right? It's x, right? It's just the solution is sine x. We all know that, okay? If you write sine of 1 over x, you say it's crazy, but it's just the wrong variable. So look, if you use appropriate variables, and yesterday Ashika was saying that the Ashika variables seem quite naturally to do that even without symmetry reduction, you can just go through, which is a strong indication that this singularity is an artifact of our way of describing things, and you can just evolve through, which, of course, if you are then in this region here, you can continue again with the Einstein equation, and you're in other. Now, of course, this has nothing to do with quantum gravity. You may expect quantum gravity to smooth out this passage here, and it's easy to imagine a metric. It's easy to imagine a metric that does that. You can just replace the radius with replace tau with tau square with tau plus L, tau square plus L, and you smooth out the singularity. You see, what's going on here is that without this L, without this regularization, the tube goes to a line, it becomes long, becomes a line, and then bounces back. If you just smooth it out, it bounces to the finite radius. In all cases, you have a metric space, but with L equals 0, you have a metric space, which is not a Riemannian space because there is a singularity in a point. You have a sort of cone, right? A point which can easily smooth out in a clessidra. So this is what's going on there. Now, it turns out that a lot of people has done the quantum gravity theory of this system here. This is a list of work in this direction, very long, as you can see. And essentially, I found that if you do the quantum gravity evolution of these degrees of freedom using loop quantum gravity in a symmetry reduced model, that's what you get. So you go through with a curvature which goes up to a maximum, finite, and then comes down. So all this indicates, I think, not from the point of view of mathematical physicists, but from the point of view of the physicists, well, that's, what happened. We just go from a trapetry region to an anti-trapetry region. And immediately you see that this is very consistent with the idea that a star can bounce, because a star enters this transition region exactly when it wants to bounce, and it can bounce because now it's an anti-trapetry region. An anti-trapetry region, you can move out. You're in a white hole, okay? Which is the answer to one of the questions. I mean, can a white hole originate from a singularity? That's the violation of the cosmic censorship. From future infinity, you look back and you see singularity. No, you don't look back and see singularity. You see the transition from a black hole, right? That's the key idea. Now, yes, but what about B? What about what happened at the horizon? Because here is a block, there is a horizon, here is a horizon. And if I glue to Kruskal space-time in this way, this is what I was doing here, I am going to a different universe, so to say. How God was so smart to create another universe just in time for this to come in? It doesn't make much sense, right? I mean, how God should be super prevident just to. It doesn't seem to work this way. So what about the B region? We haven't said anything about the B region. Well, before going to the quantum physics of the B region, there is a result which was first suggested by Hal Haggard, who I think is here in the audience. I saw him before. He said hello at some point. Which I think, I mean, we wrote a paper on that, and I consider that my best paper on the last 10 years. It's a paper in classical general relativity, and is a classical generativity result, which says the following, that there is a solution of the classical Einstein equations, which outside is just outside Schwarzschild, which continues here in the black hole and continues here in the white hole. So in other words, if this region here, it's a quantum gravity allowed transition, the outside can, the exterior of the black hole and the exterior white hole don't need to be separated, can be the same space-time. And in fact, classical generativity is consistent with the fact that there is a transition here, which takes from the black hole to a white hole, and the quantum tunneling transforms the black hole horizon into a white hole horizon. Now, how the hell is possible? Because we know that the maximal extension of Schwarzschild, it's Kruskal. So the maximal extension of Schwarzschild is just one of these things here, where the white hole in the past, the black hole is the future. So how can a black hole be in the past of the white hole? It doesn't seem to be possible this to happen, because if we can cut pieces away from Kruskal, but how can we cut away a piece and get a black hole in the past and a white hole in the future? Well, the catch is that this metric here doesn't need to be a region of Kruskal to be a solution of Einstein equation. It only needs to be locally isometric to Kruskal. So each piece of here must be a piece of Kruskal, but you can patch and glue pieces together. And so this is what you're supposed to do. You take Kruskal, you take the inside of the black hole, okay, you cut it if you want Kruskal here, and you cut it away the star. It of course glues naturally with the outside. You take the outside and you continue this way. So there's a part of Kruskal which is counted twice, but that's okay, because one is here and one is here. So in other words, this blue region here, which is the solution of Einstein equation, which I claim is a solution of Einstein equation, is a solution of Einstein equation because it's a local isomorphic. There's a map from here to Kruskal, which is not 1-to-1, it's 1-to-2, but it's locally isomorphic to Kruskal, so it's locally a solution of Einstein equation. So it's a solution of Einstein equations, right? And of course, the possibility is because you're violating Einstein equation in this region here, where you expect a violation of Einstein equation because it's a high curvature region. Okay, this is the paper where this is done carefully with all the formulas, all the equations, all the cutting, the pasting, and all that carefully. So now we have a story of what happens in the future of a black hole. The black hole forms, the star bounces through the singularity transition, and here there's a quantum gravity region which allows the black hole to continue. Now, this picture, it's built in a time reversal symmetric way. This story does not need to be time reversal symmetric. This is the first paper that analyzed the. So if you want, the black hole and white hole can have very different time durations. How am I doing with time? I'll skip the effect of the Hawking radiation on that because it's a little bit, sorry, Pierre, if you're listening, I'm skipping your work. And
question of you.
Yeah, please.
It's about these choice of different variables. It was, is there any physical insight to avoid choosing bad coordinate system that creates confusions in the physics of any system? For instance, what happens with Kruskal with respect to Schwarzschild?
No, I think that I don't see anything physically meaningful. I think it's another level, but it's the same story as the Schwarzschild singularity. I mean, if you have coordinates that say something funny is happening, it might be just you have chosen bad coordinates. So it's up to you to see if there are good coordinates. You change coordinates where you can go through and you say, oh, I chose bad coordinates. Okay, like if on the plane of the Euclidean plane you choose y plus 1 over x, of course something funny happens. Or if you want the polar coordinates, say that North Pole is funny, right? All the different phi for theta equals 0 are all the same point. but then you change coordinates and you see it's known. So I think it's the same with not the coordinate, but the variables. If you have a differential equation that describes a physical phenomenon, and the differential equation explodes, and you change variables, the variables used to describe the phenomenon are free to change what you want. And you discover that in the new variables is not an infinity, but you go through, you just say, oh, those were bad coordinates. So it might very well be that the Riemannian metric, it's a bad coordinate in the center of black holes, which, Riemannian metric is not God-given, it's Einstein given, but Einstein is not God. I mean, we already know that it doesn't work for fermions. We have to go to tetrads. So I think that's the point. I mean, there is a thing which is a gravitational field, which is described by some variables, and if we choose other variables and we see that we can continue it, that means just that there are better variable there. Now, of course, I don't want to overplay this because we do expect quantum gravity phenomena around the singularity. It's not that classical theory. I don't know how I would just trust the classical theory there, because it's high curvature. So it's very reassuring that when you do the quantum theory, you get exactly the same result.
Okay. There's a related question, but I think you partially answered it already. It is, are you saying that the singularity at r equals 0 is an apparent singularity which can disappear by change of coordinate, just as we get rid of the singularity at r equals 2m by using the costar coordinates?
Not really, because singularity is a vague word, of course. We have to define them. So if we define singularity as something that goes wrong as a Riemannian manifold, then as a Riemannian manifold, that's still a singularity. It's in that point is the metric becomes degenerate. So if the question is a mathematical question, the answer is definitely not. That remains a singularity. If the question is a physical question, I'm not sure, because I'm tempted to answer yes in that case. I mean, it might be that at least in this case, I don't want to say a general case at all, we overplayed the importance of the fact that the metric becomes degenerate. I mean, it doesn't mean that space-time dies there or finish or anything like that. It's just that the Einstein equation continue a different way, or a quantum transition continues in other ways. So yes, physically, and again, I'm not doing mathematical physics here. I'm doing physics. Physically, I think that the central singularity of black hole is less of a singular point of the universe than what we expect. Okay, so can I go ahead, Johannes?
Last question. It is about white holes, and is there any hope of finding them in some experimental hints for white holes?
That's the last part of my talk. If I get there, that's the last chapter of my talk.
Okay.
So this is a picture we have, and notice that the beautiful of this picture is that it's pretty rigid in some sense. Namely, most of it's a solution of Einstein equations. And here we've assumed spherical symmetry, so it makes it particularly rigid because of spherical symmetry. Of course, the universe is more complicated, but if we understand that, we're in good step ahead. And this metric here depends only on a few parameters, like the mass of the star that collapsed, the time, the lifetime of the black hole before something happens, before the transition, the tunneling time, the time something happens, then you're back to Schwarzschild. Then you know everything what would happen. And here the lifetime of the white hole. So in a sense, you can say, good. So space-time is determined by these parameters here. But notice that if this was a classical theory, the incoming data would be sufficient to determine everything. But this is a quantum theory, because classical generativity doesn't fix the relation to these parameters, but quantum theory should, because quantum theory should give the dynamics inside. But of course, quantum theory is probabilistic. So what we expect is that quantum theory should give us a probability of having some combination of this. For instance, that given a certain mass, how long is the black hole going to live, and so on and so forth. So what quantum gravity should give us, careful, we are in the core of quantum gravity here. What quantum gravity should give us is a probability amplitude function of these parameters here. And of course, the h bar g and the speed of light, which you can put equal to 1. So if here we have a well-posed quantum gravity problem. Find the probability amplitude as a function of m tau b, which gives the probability of this tunneling with these parameters, which in particular is going to tell me, is this going to make this transition with which probability, most likely after how much time, and so on and so forth. In loop quantum gravity, there's been a long discussion of how to interpret probability amplitudes, and we have a general way of extracting probabilities without an external time. Notice there's no external time here. There's no time here. There's a tunneling time, the black hole lifetime, the white hole lifetime, but there's no t. Here is a concrete case in which the probability amplitudes are going to ask informations about what happened at the end of the evaporation of black hole. Good. Now, what can we say a priori, just intuitively? Well, we have two arguments about the lifetime of a black hole. It should be smaller than m cube, because then the black hole is too small. And in fact, at m cube, you definitely enter in a quantum gravity region, as I said, so definitely something should happen. So one natural hypothesis is that the lifetime of black hole is in fact m cube, and nothing happens before the outside the black hole. You actually have a Planckian curvature. But it's not sure. And in fact, I've been hesitating, and in the paper with Haggard, we've put forward another possibility, which might be plausible, and I don't know, and I think is open. And is that the transition might happen much before. So T black hole might be of order m squared. Why m squared? Because, you know, what counts is not just the curvature, it's how long you stay in that curvature. Think about just a standard tunneling, like the radioactive atom. You're at a distance from it, and there's a probability of something happening. Of course, it's small because tunneling is small, but if you wait sufficient time, it's going to happen. So what matters is not just the parameters times the time, right? So it might be reasonable to think that quantum gravity corrects the Einstein equation sort of linearly, and the correction is order of the curvature over the Planck time, of the Planck scale, if you want. But since it's linear, it grows in time. So what you want is not r to be Planckian, but r times the time to be Planckian. And if you plug in, you see immediately that r, once again, is the mass of r cubed. So it's order of one of the mass square. So you get that one of mass square times the tau equal 1. So tau is m squared, right? So there's a second hypothesis here that the black hole make this transition not when it's shrunk all the way to Planckian, but much earlier, after a time m squared. This is a good argument, but not a convincing argument, not a strong argument. So we should do the calculation. We should compute this transition amplitude here, and this should tell us this. I mean, it's a probability becoming significant when tau is order m squared over tau is order m cubed. This is enormously important for astrophysical consequences, I will say in a moment. And other points, notice that definitely there is no event horizon. And I discussed why there could be no event horizon. And this quantum gravity scenarios just definitely show that you don't expect a black hole horizon. So you don't expect anything like that either, because, you know, there's no, look, all part of space-time can be seen from future infinity. So there's no horizon, there's no event horizon here, okay? Like there is an event horizon here. This part of space-time is not seen from infinity. Now, the fact is non-event horizon, by the way, is an old idea. This is a paper, this is a comment by Hawking saying there are no black holes in his usual provocative way. If you read what he meant the actual black hole in the sky don't have an event horizon, have only a trapping horizon, a dynamical horizon, an apparent horizon, which are all variation of the same idea. Now, before going to the loop quantum gravity calculation, I want to make a parenthesis about the black hole paradox. Because you see, why there should be an information paradox here? I mean, information comes in, goes through, and comes out, right? And in fact, there's even a huge volume, as one of the questions correctly indicated. There's a huge volume here. So why there's room for all the information you want and then can come out? So why people say, why people say there is an information paradox? And I want to try to convince you that the information paradox is not a paradox from general relativity in quantum mechanics or general relativity quantum field theory. It's a paradox that comes in if you take general relativity, quantum field theory, and some other assumptions, which are natural if you do ADF-CFT or if you do string theory, but are not natural at all if you just think that there is a quantum gravitational field. And to do that, I have first to remind you, if it's not clear to you, the distinction between thermodynamical entropy and von Neumann entropy. Thermodynamical entropy, this is the Boltzmann, this is a formula on the grave of Ludwig Boltzmann. It counts the number of states of a system, and this is what determines the temperature and the relation with the thermodynamical entropy, right? The derivative with respect to the energy, it's what gives the temperature. For a quantum system, roughly, is the dimension of is given by the dimension of Hilbert space on the system. The von Neumann entropy, it's something that measures essentially the entanglement. In this case, the use of von Neumann entropy here, it's a way of measuring the entanglement between two systems. You have two systems, A and B, and you have a state. If the state is a tensor state, is psi of A times psi of B, the von Neumann entropy is 0. But if generically, if you trace over B, you get a density matrix for the system A, just on the system A. You compute its entropy, namely trace of rho log trace of rho log rho for this density matrix, and you get a quantity, which is the von Neumann entropy, that measure how much this is not pure, so how much information is hidden in the entanglement with B. Now, given this clear distinction, of course there is a relation, because if B has a finite Hilbert space, its von Neumann entropy, the von Neumann entropy determines cannot be bigger than the thermodynamical entropy. So one is tempted to say, all right, so in both cases, we're just counting the number of states inside. But that's a mistake, because systems can be isolated and not exchange heat and work. And let me tell you a characteristic case, simple case, physics we understand very well, where the von Neumann entropy can be much larger than the thermodynamical entropy. And this is the case in which you have a box A, inside of which there is a box B, which at some point you isolate completely. You put, at some point, you put a screen around it, which does not allow energy to go through. So if you're outside observer and you exchange heat and work with the big box here, B is like non-existing, obviously. So your thermodynamic entropy only counts the state of A, not the state of B. But if before being isolated, you got entangled with B, then the von Neumann entropy measures the entanglement between you and B as well, even after you isolated B, right? So the von Neumann entropy can be much larger than the thermodynamical entropy. And that's exactly what happened in black holes, because interior black holes cannot send information anymore to you, so it doesn't participate to the thermodynamical entropy anymore, but it still can hold phenomenon entropy, which tells you that your state is not pure because it's correlated with something inside B. And as long, but only as long as you assume there is an event horizon, the information here is lost, but there's no event horizon. So when you move out, if you want, when you move, when you're the observer side, when you turn the corner and now you see the inside, then you see the box, and then you recover the information which was invisible for you for some times, for the period during which the event horizon approximation seemed to be good, right? So once this is understood, you see exactly where the assumption come in of all the papers that claim there is some paradox here and derive strange physics from that, like the famous firewall paradox, firewall prediction. You see, this is the abstract of the firewall prediction. And you see, there are all sorts of work out there trying to find funny solutions to this so-called paradox. And it's based on three postulates. One is unitarity at infinity. One is that essentially the generativity holds around the horizon. And the third, that's a key one, all three together brings a paradox. And people say, okay, there is a inconsistency between unitarity and the equivalence principle. But the doubt between these two is a third postulate. And where does this third postulate comes in? Is the assumption that a black hole has a number of states which is discrete and bounded by the area. So it's the assumption that the entropy, the black hole entropy, but bounds the number of states inside the von Neumann entropy. But this is wrong assumption. This is only true if you think that, sorry, I go back to the, this is only true if you think that there is an event horizon and what is inside is lost forever. And you see, the number of states of the black hole is bounded by the area only if you, by number of states, you mean the number of states that can be distinguished from the outside as long as there is an event horizon. If you do so, then there's a famous paper by Page that says, well, since the area comes in, the number of states available goes down. So the von Neumann entropy has to come down. That's a mistake. Has to come down because it's bounded. Okay. And therefore, there are not enough states inside to purify the Hawking radiation, you have to bring the information out. And therefore, people invent all sorts of machinery, you know, late Hawking quanta correlated to early Hawking quanta, strange things happening on the horizon, mystery of mystery, just because they don't consider the possibility that what comes inside, the information is there and then come out later as the through the white hole. And I have a few more detailed papers on that. I just want to point out the idea that the number of states could decrease before going into the quantum gravity regime. So the idea that the number of states on this Cauchy surface here can be less than the number of states on this Cauchy surface here, because the horizon has shrunk a little bit. And so the area is small. It just contradicts badly what we know about quantum field theory, because the algebra observable here contains as a subset of the algebra observable here by the equations of motion. So the Hilbert space here cannot be smaller than the Hilbert space here, because it's a restriction on the subspace. The states are function of the algebra. I discussed this in this paper here. So don't believe in the Page argument. It's just the wrong idea of what happens. It's all the idea that there is it's a priori assumption that the information inside is lost.
There's a question concerning this.
Okay.
It's what is your opinion on the island formula and the entanglement entropy of Hawking radiation then?
Which formula?
The island formula. Island? Island? formula?
I don't know what is the island formula. Island, like island?
Yeah, ISLAND.
I don't know. Okay. Can you say more?
Carlo, this is recent work from the string community around these sort of non-trivial topologies in the gravitational path integral.
Oh, Marolf and company?
Yep.
Um, uh, yes, I know about that. It's Marolf. They don't take string theory. They take a path integral approach and some overall possible topologies. I think it's I mean, I could discuss in detail that paper. I don't want to go into that. I think it's a lot of desperate work trying to find way out of a known problem. And there's a number of things like that. I talked with Marolf, of course he disagrees. But I don't want to go into discuss that physics. I mean, it's interesting because it uses, in a sense, he uses a quantum gravity logic, summing over topologies. I don't want to go in detail where I think is the analog of the same assumption playing a role there. The key point is that there is no problem. This idea that information, this intuition by Page that a black hole is like a fire that slowly goes to the vacuum state, so there is no more states, so all the information has come out slowly, and the late photons are correlated to the early photons. That's the wrong analogy. It's definitely the wrong analogy because the information, according to classical generativity and standard quantum field theory, namely according to the physics we know, is inside and has no reason to come out. Good. Let me go to finally to loop quantum gravity, because all this is to say that we have to compute this amplitude. And there is a number of papers that have started doing these calculations about this amplitude and answer questions like how long is a white hole living, how long is a black hole living, when this transition happening, and things like that. Now, I don't know how much of the covariant loop quantum gravity you guys have followed in the course, in the various classes. This is my one slide summary of loop quantum gravity, the way I use it. There is a kinematical part in which there are the Hilbert space constructed on graphs and the sort of spin network states. There are the operators, which have as a classical limit the gravitational field. And in the classical limit, they define a geometry, a quantum geometry. So this is the kinematics, and for us, these are the states at the boundary of the quantum region. And then there are transition amplitudes, and there are a number of ways of writing the transition amplitude, but there is a definition of transition amplitudes, which is this one, which is in 4 dimensions, is Lorentzian and is ultraviolet finite, and in some limits it connects to classical GR. This is one of the discussions. What are exactly those limits? How and in which way do we have to take some? Do we have to normalize the immediacy parameter? A lot of discussion, but these formulas can be used as they are for computing things. And the key core of this formula is these quantities here. All the rest is sort of trivial. These quantities here are the matrix elements of the SL2C unitary representations, which are well-defined functions but complicated to work with, are defined through some integrals and not easy to compute with. There is a lot of numerical work for computing this amplitude explicitly in specific cases, and they're approaching the moment in which this physical calculation can be done numerically. The calculation can be done order by order in an expansion with number of vertices. I think this is a well-defined truncation of the theory, so it's meaningful, but this has not been proved yet. So there's a lot of open mathematical physics questions here, but the theory is there and can be used to do calculation. And the logic here is that you take a quantum, a space-time region, you have the state on the boundary, okay, and you consider it as a quantum system. And so you identify the boundary of the region with a Heisenberg cut. So the distinction between the system and whatever is outside, whatever interpretation of quantum mechanics you prefer. There's always a value of something with respect to something else. So the boundary you want is, you want to go around this region here, consider everything outside classical, and consider this transition region your quantum system. You have a quantum state on the boundary, and you will compute the transition amplitude from, if you want, the past to the future. And since, how do you write the state of the boundary? Well, you know the state of the boundary because you know the geometry outside, and the state is just the geometry. So you just compute the transition, you choose a surface, which you want it not too small because you don't want to enter the quantum region. You want large enough to be in a classical, in a region where classical approximation is still good, or again good, but not too large for not complicating your life. So as close as possible to the region where the curvature becomes Planckian. So you choose a region in the space-time metric that is well defined and well known. You know the intrinsic and extrinsic geometry of this region. So now you want to use the kinematics here. There is a well-developed theory of coherent states, wave packets, if you want, that given a classical geometry, you can approximate it with quantum states in this Hilbert space here, some truncation, of course. And all this is a technical work, which is in part done, maybe can be done better. So you choose a truncation, which means finite number of nodes here. And you write a coherent state that correspond to the classical geometry of this sigma surface, again, that you know because we know the geometry outside. But the geometry outside, remember, it depends on some parameters. Where are my parameters? Here. It depends on those parameters here. So you get a coherent state that depends on these parameters. So you get the transition amplitudes between this coherent state that depend on these parameters, right? So you finally compute this transition amplitude. And to compute this transition amplitude, you have to do a spin form inside. So again, choose a truncation in a finite number of vertices, like you do with Feynman graphs, right? You go order by order in Feynman graphs. So you choose the lowest truncation that you can, because hoping that this is good enough. So you have to do some standard differential geometry. You have you choose your parameter carefully. You choose the surface. This is how the bottom part of the surface look when seen in Kruskal. You remember that that metric is locally isometric to Kruskal. So you map it in Kruskal. You write the geometry of this. You have various parameters, m, this distance, and so on and so forth. I'm not giving you the full detail. It's a beautiful technical work that is some classical geometry, some application of the spin form, of the coherent state of the spin form. This is a calculation of the geometry of the surface. This is a calculation of the extrinsic geometry, and it depends on the parameters which are hidden in the constant written here. And now you choose the discretization. This is the discretization which has been chosen so far. It looks complicated because remember, each point here is a sphere. So the topology of sigma is S2 cross S1. S1 is the circle here, S2 is point here. So you want somehow to respect the symmetry. You don't want just to put point there. So you have more points, but they're all the same, so to say. So this thing respect the symmetry, the SO3 symmetry of the rotation is broken down to a tetrahedral symmetry. Essentially, you have one sphere here and one sphere here. This is larger, this is smaller. So the larger sphere is this outside tetrahedron. The smaller sphere is the inside tetrahedron. You join, so you have, and you join twice. in the past and in the future. So you have a transition from this to this, so to say. This is the boundary, and this is the full bulk. And then you have the explicit formulas, the formulas here, and you write them down explicitly, and you get a explicit formula for the transition amplitude, which looks a little bit scary. It's here, but it's an explicit formula, and it's a function of these external parameters written in terms of some group integrals. And now, you know, if you were great mathematicians, we compute these great integrals, what is being done is to do some saddle point approximation and to go to the computer and slowly, and Pietro Donà, it's a master of this game, together with beautiful codes that has been developed mostly by Francesco Gozzini, and there are other people, the younger people in Marseille. Now it's been used by a number of young people there, trying to compute this thing here. Where we haven't any explicit formula of the transition amplitude yet. We're looking for, you know, young people willing to help, because we want to know what happened to the black hole at the end of the transition. Good. I want to leave some time for questions, so I want to skip to now. Don't want to give you more details here. I want to skip to some connection to observations and to astrophysics, and to, because that's the aim. And there are two ideas here. One is dark matter. One is more general astrophysical signals like gamma rays explicitly. The key point being that the time duration of the white hole is most likely very long. And let me give you the intuition here. Let's say that the evolution is the lifetime of the black hole is m cube. So if the m cube, the black hole is very small, which says that that's where we are very confident that the tunneling happened. But then the black hole starts very small. The white hole starts very small. That's Planckian, so a microgram. So then you have all this information here that has to come out from a very teeny microgram white hole with very little energy. So you need something which has little energy and a lot of information, and the only possibility is you have very low frequency things coming out. So it's possible, it's not impossible, but you need a lot of time for coming out. And if you put numbers in, you need M4. M4 is a very, very long time in where M is not the mass here, is the original mass of the star, because this is M cube. The information here is determined by M. So you have a very, very long living white hole, which is an old idea, that black holes at the end of evaporation becomes remnant, and a very long living remnants. It was discussed in the 80s. It was discussed various times in the past. In the past, the idea of remnants was a sort of a black box. What could a remnant be? Now, this is quite spectacular, because nobody thought it could be just a white hole. A white hole is a perfect remnant and is not an exotic object. It's an object predicted by classical generativity. Quantum gravity only plays the game of making this be born, but then it's just classical generativity to describe them. It's a very, very long tube, which in time comes back and becomes larger and larger, so to say. It reopens with respect to the size, but if you want, the star here is 10 to the 75 light years hidden there. It has to come out. That's an intuitive Pullman way of saying what's happened. And it takes a long time from the outside, which is exactly the time reversal of the story here. It's very long because it took a long time to get there. There were arguments for that convinced some people that long living remnants were not physical, but these arguments are wrong if you realize that, I don't want to go into details, that they are not strange particles, they are space-time, peculiar space-time geometries, configuration of gravitational field, which can only be produced through this complicated process here. Now,
There are only 9 minutes left, so
okay, so I'll rush. I'll only say that white hole have the property of being unstable, and I don't want to go into that if they're macroscopic. But a Planckian size microgram black hole can be stable, in fact, has to be stable, because it's sort of a bottom state of the energy of a linear combination of black hole and white hole. In other words, we have processes that transform black hole in white hole, which is what I just described. Processes that describe a transformation of white hole into black hole, which is the white hole instabilities, and a dynamics for black holes and white holes. So we have just a matrix. If you think that if you think this is a quantum object, you have a two-state system which has a minimal energy, which is stable, obviously. And so this is described in this paper here. So one expects quantum gravity to stabilize the white hole against anything, just to make them stable objects, which means that the prediction here that the longer living things which only interact gravitationally, which is one portion of a microgram all over the sky, if there were primordial black holes, small black holes to start with. And this is a perfect candidate of dark matter. The difficulty is to check this theory, but on the other hand, it's, of course, we have many candidates of dark matter, so maybe a component of dark matter. But it's different than any other candidate of dark matter because it just follows from gravity and quantum. You don't need to postulate neutralinos, funny variation of Einstein equations, just Einstein equation in quantum mechanics. The other possibility is that what fell in, it's going to come out at some point, and we could see it. And if these were created early universe, if you compute the proper time outside of one of these things is basically the Hubble time, but the proper time inside is very, very short. If you want, a black hole is a shortcut to the future. You fall into the black hole and you jump out immediately and you're in the far distant future. That's what the black hole is. So you have these photons that come out, and it's a simple calculation to show, I don't have time to go through, that these, you know how to expect the frequency of the photons falling in because you know when they were formed in the early universe. So you know the frequency coming out. And if you look at the detail of this story, you find out that the more this object explode distance from you, the younger they were, and therefore the shorter wavelength they came from. And so there is a relation between the distance when they emit the photons and the frequency, which could be detectable indirectly in the sky. And there is phenomenology, there are phenomenology papers looking for this peculiar curve, which would be a smoking gun of this. It's a very peculiar, I mean, there's no other astrophysical phenomenon that could have a flattening of a redshift like that. I just want to mention that there's Francesca Vidotto is the one who has looked more and is more in touch with phenomenologists. Aurélien Barrault has looked into various of this possible phenomenology of this this physics. As Francesca said in the discussion, it's not just phenomenology versus theory. It's physics versus mathematical physics and versus people closer to observation. I'm doing the physics. Okay, so this is my summary. I had a few other slides about quantum gravity in general, but I stop here because I preferred using the few remaining minutes to have your reaction or your question on everything.
Okay, thank you. Thank you for this nice talk. There are actually some questions. Yes, there are two remaining questions concerning what you said about the information loss paradox. One question is, does the Noether theorem still hold if two black holes with the same area can be different?
Very good question. Thank you for raising that. No, it doesn't. In fact, all this, if you want, is it's a story about the fact of not being foolish by the no hair theory. A black hole, a static black hole, is indistinguishable. Two static black holes with the same mass, angular momentum, and charge are indistinguishable only as long as no quantum tunneling happens to reveal what is inside. Right. So it's a theorem only to the extent in which you don't have quantum gravity. As soon as you have quantum gravity, you violate the theorem, because you go around the corner and you see what is inside, so to say. And in fact, the key point here is that if you have just forget charge and angular momentum, if you have a black hole at some point, a certain area, the physics of this object, if it is just produced by a small star, or if it is a long, very old black hole produced by a big star that has evaporated, it's completely different, because the inside is completely different, and it has a different quantum theory, a different white hole that comes out.
Okay. The other question concerning this is just an understanding question. It's so quantum gravity removes the singularity. Now jumped. Removes the singularity, and the black hole transforms into white hole. Then the information will be released. Thus, there's no so-called information paradox. So yeah, just as a summary of your argument. Basically.
Yes, it's that's all exactly correct. Okay. That's all exactly correct. The subtlety is that if you present the story to all these people who deal with the paradox, they would say that the paradox comes before the quantum gravity region because of the argument by Page. So before the quantum gravity region, when the black hole starts shrinking, already there is a problem, they would say, because the black hole does not have enough states inside. So the information must have come out somehow. And this, it's wrong if it is presented just as a consequence of quantum field theory and generativity. This is a consequence of an hypothesis, which is a sort of strong version of holography, that the number of internal states of black hole, it's bounded by the Hawkins, Beckes-Hawkins entropy, namely by the area. And this hypothesis is only justified by the fact that people are in love with Maldacena idea that you describe everything at infinity, and you just and a black hole is an event horizon, and so you only see the boundary, so to say. You don't see the internal. There's no internal in that logic. I think that logic is wrong. It's just wrong. If you want to describe everything from the boundary, I'm not saying it's not possible, but you have to keep into account that black holes are not event horizons. Real black holes are not event horizons.
Okay. Yeah. Actually, our time is is actually over, but there are 3 more questions I think we should discuss.
Yeah, absolutely. I'm happy to continue.
So the next question is about the computation of this transition amplitude, and it's about the intersection of the blue part and sigma. And I think this was one of your graphics. And the question is, naively, it cannot be closed there, and if that is a problem.
The intersection
was a few slides before.
Oh, sigma. Here or in somewhere else?
I think it's that picture, and yeah, the blue part B and sigma, and basically if they are far away from each other, and if there is a problem.
Good. So think about the standard story in quantum theory, just non-relativistic theory. If you have a quantum system, it interacts with something. You can always consider what it interacts with quantum, right? You can always consider your apparatus quantum. So you can always move your boundary between quantum and your measuring outside. you cannot go too inside, because if you go too inside, you're missing quantum phenomena. You're assuming that something classical and instead of quantum. So the story here is that you want sigma to be outside the quantum region, and it can be outside as you want, but you don't want it to be large, because the more large it is, the more degrees of freedom you have to compute. It's like, you don't want to do the quantum mechanics of Olsten-Gerlach apparatus, because it's horrendously complicated. You just want to do the atom. So sigma must be outside the region where we expect quantum gravity, but as close as possible to it. That's a recipe for fixing it.
Okay. Thanks. Then there's the question if region B can actually be computed with a symmetry reduced model instead of using the full theory. So using spherical symmetry instead of the full theory. Oh,
I don't know. That's great question. I don't know. Maybe you're honest. You might.
Yeah.
I'm not aware of that. People try to put all the. Yeah, I don't know. It's a good research program. I don't think anybody has thought that for the moment.
So then there is the question, does the typical black hole thermodynamics extend in some form to its maximal picture with a black and white hole glued together?
Well, the standard black hole thermodynamics, obviously not, because it's really predicated on black hole being static things, so nothing happens forever, and it predicated it's being really classical all the way through, and existing an event horizon. So standard black hole thermodynamics does not go through. It goes through, of course, as a good approximation, as long as you don't turn the corner and see what is inside. But so if this was a question, the answer is no. But of course, I suppose the question is more deep, and is can we extend black hole thermodynamics to make sense also of the white hole part, and to describe this transition? And that's another super good research program. I don't know. Maybe yes. Maybe there is a way of continue talking about. Continue seeing this entire thing as a thermodynamical system that is slowly cooling, because that's what is happening. I don't know. Nobody has looked into that yet. Of course, all this black to white transition story is a development of the last, I don't know, how long, Hal? 5 years more, something more, just going slowly. So there's a lot of very good foundational open questions like this one, which are nobody has looked into them yet.
Okay, I think there's one last question, which is actually 3 questions, if I understand.
Okay.
So why does it seem like the spatial slice considered at r smaller than 2m are some points closer to the singularity than other on the diagrams considered before the break? Does this have any consequences? The second question is, from what I learned today, white holes emit particles. Why don't we observe it? Is it because the observable size white holes haven't formed yet? And the third is, can a black hole be glued to the end of a white hole and there's a cycle of these events?
Okay, so the first one, I think I know the slide it refers to. Where is this? Here, maybe. So it's it's this blue line here, right? It's being this is a line where we somehow, this is a line where the curvature becomes Planckian. So in principle, you can just write it down and compute where it is. including the fact that the horizon is shrinking, is slowly shrinking. That's why it leaks out of the horizon. But it can be easily broken in two parts. I mean, you can look at what happens away from the horizon, and then you can look at what happened near the horizon, around the horizon itself. That's the more complicated things, because that's a sort of a, if you think that this happened when the horizon is Planckian, this is a dynamical situation. So the metric's changing sort of rapidly in this corner here. So you have to do something complicated. If you want to look at what happened there, and that's where the picture of the tube come in, the easiest thing is to just here. The easier thing is just to forget this piece and here take a constant r, because for most of this this thing here, and remember, we are looking at 10 to the 75 light years of length here, right? So for most of it, it's nearly constant in the x direction. So you can think that there is a symmetry in the x direction. Of course, it's not exactly constant because there's Hawking radiation falling in and changing the mass slowly. But if you forget that, you can take r equal constant. So this is at the same, all at the same distance, the same proper time from the singularity. Remember, this is trying to build a physical picture of a complicated phenomenon. One of the things I skipped is the work of Pierre, who has computed the effect of the Hawking radiation on the metric. And so you see that the mass, this is a singularity, and the color is the local mass. So locally is like Schwarzschild with a varying mass. And you see it varies slowly. And I even have a slide with the actual computation of the metric in each one of these regions. Which can be done, but it becomes complicated if you want to do it. And also this is an approximation, because we don't have an exact expression for the back reaction of the Hawking. So this is done step by step into describing a complex phenomenon, each piece with its own where the approximation is good. So the blue line is sort of constant all the way, a fixed distance for the singularity, until toward the end it turns out to exit the horizon. The second question was about observing white hole. Well, one possibility could be that we're in the same situation of black holes. I mean, for black holes, we're observed in the 30s. The signal from the Sagittarius A star, colossal black hole, was disturbing communications, transatlantic communication for years. Nobody thought it was we might be in the same situation. Maybe dark matter is just a lot of little white holes. It's a possibility. Maybe yes, maybe not. So maybe there is already a observation. For the moment, nothing. It's clearly none of the, there are many gamma rays. We don't know their origin. There are many things out there. At some point, I got pretty excited that fast radio burst could be related to, because if the transition time is m squared and not m cubed, there is a natural, I don't have time to go into the story, possibility that the emitted signal is a strong burst in the radio, and these are observed. But now there seem to be better explanation of radio burst. So we are in this situation in which we don't know about white hole signals, anything for sure. And the last question, no, I mean the end of the white hole, it's at least in this model, is just like the collapse of the star. I mean, the white hole dissipates by all the information of the energy inside coming out, and then classical generativity tell us that a black hole can just ends. Like classical generativity tell us that a black hole can start, a black hole can end the same way. In fact, it's the same equations with t going to minus t.
Yeah, sorry, I missed it. This was already the part about the gluing the black hole part of the white hole, right?
Yeah, the third part of
Okay.
the question.
Yes, then there are no more questions, and I think we are also now good enough over time.
Okay, so great. I'm sorry we couldn't have a more, direct exchange. Don't hesitate to write to me. Maybe I'm not going to answer immediately because, of course, I'm overwhelmed by mails. But I appreciate if you have question or anything, and I hope next school we can do in person and have direct interactions. I think you can easily find my email address. Just Google my webpage if you have any doubt. And remember, the 3 books are all free on my webpage. Here are the my book.pdf, introduction quantum gravity.pdf, and grpdf.